Hello students, my name is Patra and I'm assistant professor in civil engineering department from Haldia Technology. Today I'm going to teach you cement. What is cement? So let's start. It's nothing but as a treatise binder. It is properly as a building material and materials with adhesive and cohesive properties. The adhesive means the attraction between different type of molecules, and cohesive means the attraction between the similar kind of molecules. Okay, so it is a kind of binder. Okay, so it binds together with the sand and coarse aggregate together. Coarse aggregate means it means the stone chips, stones, sort of small stones at 20 mm diameter or something 10 mm diameter, whatever, depending on the mix calculation. Depending on the strength required, it requires to calculate the mix design. Okay, to fill voids between sand and coarse aggregate particle to form compact masses. It is known as cement. And it has two types of it has mainly two types of cement. Let's say hydraulic cement and non-hydraulic cement. Non-hydraulic cement is that would not set or harden in water, and hydraulic cement at set and harden in water. Example is a Portland cement, and example is a plaster of Paris. Non-hydraulic cement example is a plaster of Paris. And Portland cement mainly consists of SiO2, which is abbreviated as S, and Fe2O3 ferrite, which is abbreviated as F, and Al2O3 alumina, abbreviated as A. This is the nomenclature in civil engineering, is not nomenclature in chemistry. Okay? So remember it because it will be helpful in the future lecture. And limestone chalk, CaCO3, calcium carbonate, abbreviated as C. This mixture got heated and it forms a clinker, and clinker then grounded to powder. That powder is packed in a bag, 50 kg bag, and that is sold and market. Okay, and it is defined as the product obtained by finally pulverizing clinker metal. That I already told you, with fusion of aluminum silicates and calcareous materials. Clinker, what is clinker? Clinker is nothing but the fusion of different type of aluminum silicates and calcareous material. This is fusion. It looks like this type. This is a clinker means it's a larger particles, and whereas in the cement bag we got a finer particle. These larger particles get which is produced in the in the factory, cement factory, and that we grinded it and packed in a bag. Okay, this is 3 to 25 mm diameter, mainly 3 to 25 mm diameter. It gets, I already told you this is a fusion of aluminum silicates and calcareous materials. Okay, this is the cement. Bottle cement. Cement is made by heating limestone, calcium carbonate with small quantities of other materials such as clay to 1450 centigrade in a kiln. Kiln means it's a chimney type material where in the ground we heat the materials, calcareous material and algareous material, and that it forms in a clinker form, and that when that clinker is grounded in a powder form, that powder we packed in a cement uh, bags, sacks, and then we sell it. This with the help of calcination and this with the help of calcareous compound, and the calcareous compound is we heated at 1450 centigrade in a kiln, which is known as calcination, and whereby molecule of carbon dioxide is liberated from the calcium carbonate to form calcium oxide or quicklime, which is then blended with other metals that have been included in the mix. Chemical composition, it is a raw materials, and later I will state you what are the various percentages. The fundamental chemical compounds to produce cement clinker are lime, CO, silica, SiO2, alumina, L2O3, iron oxide, Fe2O3, magnesium, sulfur trioxide, alkalis. The raw materials in the production of clinker cement, types of raw materials, sources of calcium carbonate, limestone, marl, and chalk, sources of algareous material. I told you this is a calcareous material. This calcium carbonate and the calcareous material, limestone, marl, and chalk, and argillaceous compound are clay, shale, sand, iron ore, mills, bauxite, disposal, diamond, sterolite, etc. And waste materials such as bottom mass, foundry sand, metallurgical slags, and we also put in the cement it's at certain percentage to make it environmental friendly. This waste material. Okay. And this is the typical constituents of Portland cement. This is a this CO, this is a calcium oxide, which control the strength and soundness. Strength soundness is nothing but a comp means, I mean to say, it is a mm, means expansion, means in which way it expands, in which way it contracts. In good material, a good cement, a good cement should not contract also, should not expand also, because in expanding it may crack, or in contracting it also may crack. That is soundness. Okay, soundness means expansion. Control strength and soundness. Strength soundness means expansion. It controls the expansion. Okay, due to heat, due to the high amount of heat produced in the during the process of hydration. Okay, I will teach you later what is hydration. That is a chemical reaction between cement and water. Its deficiency reduces strength and setting time. It has 60 to 65%. That is, and next, consider silicon oxide SiO2 gives strength, and excess of it causes slow setting 17, 20 to 25%. Aluminum oxide Al2O3 responsible for quick setting if in excess, lower strength 3 to 8%. Ferric oxide Fe2O3 gives color and help in fusion of different ingredients 0.5 to 6%. MgO imparts color and hardness if in excess, causes cracks in mortar and concrete and unsoundness due to 5 or 0.5 to 4%. And Na2O, K2O, TiO2, P2O5. These are residues if it in excess cause fluorescent cracking 0.1 to 4%, 0.4%, 0.1 to 0.2% respectively. And SO3 that makes cement sound, that is 1 to 2%. Okay. Compounds formed in the burning process which have properties of setting and hardening in the process of water, known as box compound. Okay, these materials, these types of materials, these materials got burned at 1450 degrees centigrade, and thereafter it forms clinker. Okay. In that clinker, the constituents of clinker is nothing but a box compounds, various box compounds. And these are the box compounds, which is trisilicate, that is 3CO.SiO2. I already told you this, please remember it, because CO I abbreviated as, in civil engineering abbreviated as C3S. There's nothing, abbreviation means nothing but a nomenclature in civil engineering. Okay, it is type of nomenclature, not a particular nomenclature. CO is abbreviated as C, SiO2 is abbreviated as C3S, and it's a common name is elite. It has 45 to 75%, and dies calcium silicate 2CO.SiO2, that is 2 stands for C2, CO stands for C, SiO2 stands for S. It is C2S, which is belite, whose common name is belite, and it has 7 to 32%. Tricalcium aluminate 3CO.Al2O3, that is C3S, belite 0 to 7%. Tetracalcium aluminum ferrite 4CO.Al2O3.Fe2O3, that is C4A, because 4 CaO as 4 and L2O3 as 1, A and Fe2O3 as 1. Belite at 0 to 10%. CSO4.2H2O, CSH2 to 10%. These are nothing but a complex compounds, which is your constituents of clinkers. Okay. Okay, let's talk about some box compounds. There are 4 main box compounds, 1, 2, 3, 4, which is yes. C2S, calcium dicalcium silicate. It's slow the strength, slow strength gain, responsible for long-term strength after a year or more, 25 to 40%, approximately percentage of OPC. It's a different percentage for different kind of cements, because we treat OPC as a benchmark of a cement, because it is a most common form of cement which is used in bridge in engineering and bridge construction. It is a high strength, and we treat OPC as a benchmark. So, and these constituents are for only OPCs only. These constituents are for OPCs only. Okay. Uh, Tricalcium silicate rapid strength gain is responsible for early strength. Example 7 days, 25 to 50% approximately. percentage in OPC, 500 joule per gram heat of hydration. Tricalcium aluminate, quick setting, controlled by gypsum, susceptible to sulfate attack, 5 to 11% approximately percentage in OPC, at 65 joule per gram heat of hydration. Tetracalcium aluminum period, little contribution to setting of strength, responsible for gray color of OPC, 8 to 14%, approximately percentage OPC, 420 joule per gram heat of hydration. This is the heat of hydration 420 joule per gram. This is the heat 60 joule per gram heat of hydration. For tricalcium silicate 500 joule per gram and 260 joule per gram. And the main thing about this that it slower the gain strength, it rapidly gain strength, and quick setting. This tricalcium aluminate as quick means it's responsible for quick setting, and C4F is nothing. It has no responsibility. It's nothing responsible for strengthening of concrete, and it's very little responsible. But mainly it is used for gray color of OPC. Okay, but it comes because it has no useful of C4A, but it comes during the production of cement. C4A produces. It is a box compound. It is a complex compound, so we need to take it. But it is a useless compound. Tricalcium silicate C3S. And another base refurbished it. I mean to rephrase it. These four complex compounds. This is tricalcium silicate, best cementing material. This is best cementing material. Makes clinker easier to grind. It increases resistance to freezing and thawing. Hydrates and hardens rapidly, and is largely responsible for initial set and early strength. 70. Portland cement with higher percentage of C3S will exhibit higher early strength, and in the initial setting time early strength 7 days. Okay, higher percentage of C3S will exhibit higher early strength. Higher content will increase heat of hydration and solubility of cement. And let's talk about C2S. C2S hydrates and hardens slowly and is largely responsible for strength increase after a year or more. It is largely responsible for strength increase slowly, hardens slowly, and responsible for strength increase. Okay. Impact resistance to chemical attack, increase in contact will make clinker harder to break and reduces early strength. Reduces resistance to freezing and thawing. Reduces resistance to freezing and thawing at early stages. Okay. So tricalcium aluminate, C3A, hydrates and hardens the quickest. It is the quickest, hardens the quickest, and almost at early stage. It's a form it used for quick strength, quick setting. As high heat of hydration results in cracking of cement due to volume changes, higher content reduces setting time, weakens to sulfate attack, and lower ultimate strength. As high heat of hydration. Let's talk about tetracalcium aluminate. Is nothing. Is a useless compound. I already told you. It's a very little to strength. Contributes very little to strength, and porous cementing value. It doesn't have any value. Okay, higher content. Rather, it reduces the strength. Higher content reduces the strength slightly because box compound is very much essential. Okay. So manufacturing. What is the? Let's talk about the manufacturing process. How it's manufactured. It has mainly two types. That is one is wet process, and one is dry process. Okay. I told you it forms clinker, and that clinker we grind it in a powder form, a very fine powder form, and then we pack it in a sack. Okay. Let's talk about wet process. Difference between wet process and dry process is nothing but in the wet process we make it slurry, and that slurry we burn it, and therefore we create clinkers. Okay. The mix will be turned into form of slurry. See, this is raw materials. Raw materials. What are the raw materials? That is CO, SiO2. That raw materials. I already told you. Okay. This type of raw materials. I'm showing it again. This raw materials. This this raw materials. This raw materials used for creating cement in this raw materials. Okay, that raw material I've already told you. That raw material is divided and with yeah, mixed with water and form a slag. That raw material homogeneous crushing and grinding, and 80% of raw material pass through 20 number 200 80% of raw material pass through 200 number 200 and then we mix it with water and makes it a slurry. Okay, by adding 30 to 40% of water. 30 to 40% of water. It is heated about 2750 Fahrenheit or 1510 degrees centigrade in horizontal kilns, and it has 76 that speed has 76.153 length and 36 reversing 4.1 meter diameter. Natural gases, petroleum and coal are used for turning, and high fuel requirement make it uneconomical compared to dry process. Okay, so wet process is a diagram of wet process. Is a slurry is coming in a kiln, is a horizontal kiln, and it is um, calcinating and sintering. And then this is the clinkers. These are the clinkers, and we make it grind it and therefore and uh, pack it and sell it. And the dry process is raw materials are homogeneous, crushing, grinding, and blending. Approximately 80% of raw materials sale and pass through 200 mmc. 80% raw materials pass through 200 mmc, and mixer is fed into the kiln. And the difference is that in the dry process we mix it with water, 20 to 25% water. Okay, and but in the dry process we don't mix water. We don't mix it water. It and doesn't don't mix water and don't make it slurry. But in the wet process we make it slurry, and therefore I'm putting the kiln. Okay, in it is this process provide considerable savings in fuel and water is, and but it is most dustier. But in the dry process it is most dustier compared to the wet process. That is more efficient in grinding. In grinding, that is more efficient. The wet process is more efficient, but for dry process, it is the the production of heat. That is this heat we require less fuel, but in the wet process we require more fuel to burn it. Okay, this is the diagram. This is a blended dry feed. That is a blended slurry. That's the difference between wet process and dry process. Okay, please remember it. And 900 degrees centigrade approx clinkering, and from this is the clinkers, this is the clinkers. Okay, and this clinker will be grinded in a powder form and we pack it and sell it. This is a broad form of diagram. That is a short form of diagram. The stack electrostatic precipitors, preheater tower, raw materials, and this air clinkers, cooler, air flow, raw materials clinker. This is the process. This is the process, but this is not required. It's not so much required. Say this. So in the quarry phase, we dig it the limestone and we load it in the quarry, and therefore we take dumper and blasting and crushing and conveyor, and that therefore transporting the storage to the plant. This is the three parts: blasting, transport, and crushing and transport. So in there raw material, this raw grinding, and therefore we burning. The raw materials are very finely grounded in order to produce a raw mix. Burning the raw mix is preheated. If it goes to the kiln at 2000 degrees centigrade, somehow 1450 or 1560, it depends on the uh, depends from depends on various raw materials. what kind of temperature we require. The raw material, the raw mix is 15 degrees centigrade, and that's we for producing the clinker, and that clinker is got crushed or grinded in a powder form, and then that powder form, in that powder we packed in a sack and we sell it as a form of cement. And for grinding and storage, packing and dispatch, I already told you that clinkers we grind it. The clinker and gypsum are finely grinded in the pure cement, and other cement additives for making blend. Side other cement additives like that G flyers, bottom mass, different things. Okay, and after the storage, packing and dispatching. Okay, I think you understand this. These stages of burning in kiln, rotary kiln, first stage, second stage. It's a broad form of, but I already explained it how it's manufactured, cement is manufactured. But in the broad form, and rotary kiln is one of the most important component of cement factory. The diameter is in the range of 3 to 8 meter, lined with the refractory. Refractory is nothing but a where we it's a form of a the bucket where we cook the raw materials. Okay, so the refractory is a bucket where we cook the raw materials. Materials are mounted on a roller bearing inclined at about 3 degrees. Length of rotary kiln is in range of 30 meter to 200 meter. It is fired from lower and in using hot coal, oil or natural gas. First is dehydration zone up to 450 degrees centigrade. Here moisture is driven, and second is decomposition or calcination zone. It's a dehydration zone, and second stage is a decomposition calcination zone. At the end of this zone, the mix consists of oxides or the four main elements, that is CO, SiO2, Al2O3 and Fe2O3. Third stage is a solid stage reaction zone, where here the CO reacts with the reactive silica to form C2S, and in this zone we get box compound. Okay, in the third stage, that CO reacts with the reactive silica and forms C2S. Intermediate C3 and C4A are also formed. These two are for the fluxing agent and allows C2S to form. Okay. Fourth stage is clinker zone. This is the clinker zone where we got clinker. The hottest zone where the most important compound C3S is formed. C2S plus CO to form C3S. Clinker is complete when all the silica is in form of C2S and C3S crystal with the amount of free lime is less than 1%. Cooling zone, as clinkers move down, liquid phase solidifies and C3 and C4A crystals are formed. Same thing, I already explained it. It's a rephrasing of material, rephrasing of the process. Okay, please go through it. Okay, let's talk about field test. We have less time, so I'm skipping some slides because it was already taught you. Because field test is as a color, physical properties, presence of lumps, and strength. These are in cement. There are two types of tests. One is field test and there is laboratory test. So talking about field test, there are four types: color, checking physical properties, presence of lumps, and strength. Okay. Color should be uniform. It should not be uniform. And typical cement color is gray color with lighter greenish shade, and it gives indicator of excess lime, clay, and degree of burn. And physical properties: feel smooth when touched or rubbed in between fingers. If felt rough, indicates adulteration with sand. If hand is inserted in cement bag, hand feels cool, not warm. If it is immersed in water, it should sink and it should not float. Okay, these are the physical properties. Means I mean to say, if it is warm, if it is warm, then the cement is good. If it is cool, then the cement is bad. If we put hand inside. Okay, solar, it should be free from hard lumps. It is due to the absorption of moisture from the atmosphere. If bag contains lumps, it should be rejected. It is a laboratory test. In the laboratory test, first test is fineness test. Fineness test has three versions: sieve method, air poverty method, and sedimentation method. Okay. Condition affecting fineness, chemical composition, degree of calcination, time of grinding, the character of pulverizing machinery. Fineness of cement is a measure of size particle cement. It is expressed in terms of specific surface of cement. Most important factor that will determine the properties. Process of hydration, it's a big process. I will teach you later because the time is less. Fine cement bleed less than coarse granular, and finer grinding is increases the speed with which various consisting constituents reacts with water. Fineness of grinding is of some importance in relation and workability of concrete. Greater fineness increases the cohesive of concrete mix. Finer grinding reduces the chance of bleeding concrete. Finer cement, more is the strength of finer cement. Sieve method. Let's talk about the sieve method. Finer cement is more strength means more finer, the more strength. Okay, sieve method. Sieve is conducted with the standard PS number 9. 100 gram is taken and sieve for 15 minutes, and the residue left is not exceeded the values, the permissible values. Okay, ordinary Portland cement is 10. Percentage residue for these values are should not percentage residue of by weight should not be 10, and the for rapid hardening cement should not exceed with 5, and Portland polymer should not exceed with 5. Okay, so this is the value. The residue left should not exceed the values. With what values? These are the values. Okay, consistency test. There are the two tests. I will teach it later because time is less. Consistency test, it is used for determining the percentage of water required for preparing cement paste. Procedure: take 300 gram of cement, add 25 to 30% of or 90 gram of water, and mix water and cement on a non-porous surface. And it is used in a Vicats apparatus. Okay, this is Vicats apparatus. Well, the question comes rapidly. I mean, it's a common question from the consistency of cement. The apparatus used in the for testing consistency is Vicats apparatus. Okay, this is the look of Vicats apparatus, and let's talk about this. This is the um, skeleton diagram. That is the true diagram. Okay, and here this thing is Vicat apparatus, and this is the plunger. This is the plunger, a 10 plunger. This is the for uh, needle for final centimeter is a angular ring. Okay, and this is the 1 mm plunger. This is also plunger. Okay, okay, okay. Okay, let's assume it. It's a setting time, and basically in setting time also it's a two types of setting time: the initial setting time and final setting time. And this setting time and consistency of both have the same apparatus, that is Vicats apparatus. But the thing is that the plunger is different. Okay, see, let me see the plunger. This is for initial setting time, and this is for this is for initial setting time, and this is for consistency test, and this is for final setting time. Okay, this is for initial setting time, and this is for consistency test. Sorry. Okay, cement paste setting time is affected by by a number of items, including cement fineness, water cement ratios, chemical content, special gypsum content, and admixture. Setting tests are used to characterize how a particular cement paste sets for construction purposes. The initial setting time must not be too soon, and the final setting time must not be too late. Normally, two settings are defined. For initial setting times, normally it's 30 minutes for OPC, and final setting time normally it's OPC for 10 hours. Okay. Initial setting time occurs when paste begins to stiffen considerably. And final settling occurs when the cement hardened to the final point. That means it can sustain some load. Okay. The time of addition of water and the initial fermentation stage also refers to the time of state of changes of the cement paste from liquid to rigid stage. The setting process is accompanied by the temperature changes and hydration results in the formation of gel around each partition of the cement. The means of controlling the rate at which the cement stiffens by ingrading a measured quantity of gypsum. Okay. And initial setting time defined as the beginning of the noticeable stiffening in the cement paste. It corresponds to a rapid rise of temperature. Normally it takes 45 to 175 minutes, but for OPC it is normally 30 minutes also. You know why it is written 45 to it may differ from cement to cement types of cement, but for OPC it is 30 minutes. Okay. Final settlement refers to the compression cycle, which corresponds to the peak temperature of the cement. The stiffening of cement paste increases as the volume of gel increases and the stage at which is compared the final hardening cement. Normally, it takes 3 hours to 10 hours for this to happen. Okay. Hardening refers to the gain of the strength of the cement paste, and during the cementing time, the cement gets very little strength. And what is the procedure? A neat paste is required for with 0.85 times required to give paste a normal consistency. A normal consistency means I need to define normal consistency first, because for normal consistency we make it paste, and we filled that we filled the cement paste in this cylindrical mold, and we pass the needle 1 mm needle square. This is the 40 mm this 40 mm this is 40 mm height. Okay, 40 mm height. It is already written over here. Okay, 40 mm height, and this needle is placed above the just above the mold, and this is the indicator. This is the scale. This is the scale. Okay, this is the scale. Okay, this is the scale. Okay, your scale is an indicator, a scale also, and we remove here. It is the lock over here. It is the lock and movable rod. This movable rod, and it is locked above, just above the mold, just above the mold, and after that we remove the lock over here, and freely we freely let it move, this movable rod. We freely let it move, so that this entire rod, along with the needle, 1 mm square needle, get inserted inside the mold. Okay, at what at what percentage, means we make some percent, we make the cement paste at some certain percentage. At what percentage this reading has 6 to 7 mm, that percentage of water required to make it cement paste is known as consistency. Okay, let it consider as P. Okay, and see this needle, this 1 mm needle, we let it move freely inside the mold, and it resists. It has some resistance in it. Okay, right? It has some resistance in it, so it will, if the needle got inserted up to this base, then the water content is too much high, so we need to reduce the water content to make it simple. Then we need to re-experiment it. It's a heat and trial method. Okay, and for cement paste, for we take 0.85 times the water required to a normal consistency. That percentage of consistency, what I told you, that to make it 0 to say 6 to 7 mm height in the scale, in the Vickert separators, for with using the 1 mm needle, we we require, for that percentage, that percentage we gain from that experiment, from that percentage we take 85 percentage of water. Let's say 0.85 tons of water. 0.85 tons. Suppose the consistency got 30% of water required for making it consistent. So we need to take 85% of 30%. Okay, and start a stopwatch, adding water to the cement. Fill the mold with the cement at the level. Place the mold and lower the needle at the surface. Okay, release the needle quickly and it penetrates. See. Okay, for this is the 10 mm die. Okay, let me erase it. This 10 mm dia plunger is used for making for experimenting the initial setting time. Okay, for we replace this 1 mm square needle with this plunger 10 mm needle plunger, and we feel that it is a footable and it is a removable. Okay, this plunger is removable. We remove this 1 mm needle and fix this 10 mm needle over here. Okay, and we just replace it, and at 0.85% of water we just placed over here and release it freely. It is a lock over here. It is a lock over here, and we relock it. Means we don't relock it. We just remove it. Remove the lock so that it freely moves down. Okay. The same experiment over here, but the needle is different. For consistency test, we take 1 mm square needle, and for the for initial cycle we take a 10 mm jar. Okay, and we release it, and after releasing it, the scales would be 5 to 6 cm, 6 mm, 5 to 6 mm. Okay, 5 to 6 mm. So and we remove it from the downside, the from the downside, from the base, the height of the the height of the plunger should stop at 5 to 6 mm. 5 to 6 mm. Okay, 5 to 6 mm. In the same case, consistency is also it's with the plunger should be resist at 5 to 6 mm. But for the case of initial sector, the plunger should for the plunger should remain at 5 to 6 mm from the base level. Okay. And similarly for the final setting time, but final setting time is also we use 5 mm angular ring, and just we freely move it after 10 hours or whatever minute, just it has a impression, just impression. Whenever when the impression has got over it, then that time is the that after the we record the time. We record the time from the initial setting time to up to the final setting time. Okay, from that time, the time gap to give it a just impression. That time gap is known as final cycle. And the time gap for to the time gap required to make it 5 to 6 mm resistance from the below, that time gap is known as the initial cycle time. Okay, am I clear to everyone? I think so. Okay. Okay, thank you very much. I think let us stop here, and I will teach at the next class. From the next